Okay, so everything we've done so far has been fairly straightforward, hopefully. And the reason for that is because they were specific examples of, like special cases, I guess, of a more general differential equations. Okay, so we're looking now at the more general case. So it's all about pattern recognition. So you need to be able to recognize this format of a differential equation. Now, up until now, this left-hand side has fitted the product rule, or we've been able to rearrange so the left-hand side fitted the product rule. Now in this case, yeah, that's only going to work if, we've got a 1 here, haven't we? So if I differentiate 1, do I get p? Well, no, so that's not going to work. So if I make that direct comparison with what I've got for the product rule with this, which is the left-hand side that I did have, you can see that if you just look at the left-hand side, focusing on that, comparing it to this, the thing that's missing is a function of x in front of dy by dx here. So if I start with my original generalization, so it's just important to mention that p and q are functions of x. Okay, so it's not just a constant, this is a function, this is a function. So if I want this to fit this format, then the first thing I need to do is to times everything through by f of x. So that gives me f of x dy by dx plus f of x p of x, as it were, y equals f of x times q of x. Now, if I'm comparing this to this, now the only way that is going to be true is if this bit here is equal to this bit here. So if f dashed of x is in fact the same as f of x times some function of x, then it's going to fit that same model. So I want to try and make that true. So I'm looking at f dashed of x needs to be equal to f of x p of x, divide through by f of x. Now, in an attempt to try to do something with this, what I can actually do is integrate both sides with respect to x. So that gives me the integral of f dash x over f of x with respect to x, and the integral of p of x with respect to x. And so this is something we've not spoken a lot about yet, but will become quite crucial in core 4, when it comes to integration. This is the holy grail of integration, trying to recognize this. And you have done it from a differentiation point of view, so you should be able to see the connection with that equaling log f of x. And then this over here, I can't actually do anything with that at this moment, so it stays there. Now, there's thinking that I'll probably need a constant, but actually, because I'm going to ultimately integrate again at some point to solve the original differential equation, I can ignore that for now. So to find out what f of x is, so that I know what I've got to be able to times through by up here, at the start, I need to take exponentials of both sides, which then leads me to f of x is equal to the integral of p with respect to x. So if I've got a differential equation of this format where it doesn't fit the product rule, is not one of our special cases such as these where it was already exactly the same, or indeed something like this where I can very quickly and very obviously rearrange it so that it does fit the product rule exactly, I need to think about and consider, if I can recognize this, a function f of x which I can times through by to give me then an equation that matches. And if I'm going to do that, then that function of x has got to take this format, and this is called what we call the integrating factor. So solving differential equations by using an integrating factor is a standard and recognized method, and that's how you go about doing it. So you'd times through by the integrating, you'd figure out what the integrating factor was using this quotable result here. You would therefore be able to relate it to the product rule, and you'd be able to solve the problem in exactly the same way as we did the previous one.